and I wanted to welcome everyone to the MVD Hydrologic Engineering, Statistics and Risk Subcop webinar. And I want to welcome you all, and I want to give a very special thanks to our speakers today for sharing with us some tips on HMS model calibration. Just this presentation is brought to you by Tom Brower from HEC and Emily Moll from the St. Paul District. And I'm just going to give you a little briefing on their backgrounds and also just kind of the order. Tom's going to give you a little bit of front-end information that he usually gives at a HMS training class, gives you some background on calibration. Emily's going to bring some more hands-on and specific tidbits from her work with HMS calibrations that she uses in teaching people to use HMS, especially on the swim side. And then it'll hop back to Greg to close things out, and he'll give a little tip on some of the tools and tricks that are coming with HMS in the new versions. All right, Tom is the lead developer on the HMS team at HEC and gives a lot of these presentations in the HEC training classes. Emily Moll, she is a senior hydraulic engineer at St. Paul District and has really worked a lot with HMS development for the SWIMS program. She does ADH modeling, so she's got and VUSA modeling and has a wide variety of modeling experience there. But she's able to really communicate clearly on the how-tos and makes it really understandable for people, especially hopping onto new SWIMS models that are brought to the district. With that, I'm going to turn it over to you, Tom, to take off with the presentation.
All right. So just to check, you can hear me and you can see the slides. All right.
I can hear you on the slide.
All right. Cool. Well, then we'll get rolling. I'm going to have, so here's my video now. See me while you can. I'm Tom Brower. And now I'm going to cut out the video while I give the presentation. Okay. Video off. And so we're going to talk a little bit about model calibration. And like Ann said, the first couple slides are going to be from our HMS Basic training class, so you might have seen some of this before. A lot of this conversation is going to be in the context of real-time forecasting, so I'm going to try and tailor the content for that. We always start the calibration lecture with a little bit of theory and model classification. I have to kind of minimize that based on time today, but there's just a few things that are worth discussing. And so just a little bit on model classification. The mathematical models, like the ones used in HMS, can be classified in a number of ways. And while you don't have to know the ins and outs of the different classifications to do modeling, it's helpful to know these for calibration and know like what parameters you're changing and why you're changing them. So a little bit of knowledge of classification is important. Here's some common classifications used in modeling, and anytime you're in the modeling world, you'll hear these terms. Event and continuous is one we'll talk about a fair amount today. Spatially averaged and distributed, that's another way to classify. Empirical or conceptual, deterministic or stochastic. This is a measured parameter or fitted parameter is another one we'll talk a little bit about today. So with that, let's talk about calibration. So calibration defined. Calibration is the estimation and adjustment of model parameters and constants to improve the agreement between model output and a data set. So here's just calibration illustrated. You see on the left, pre-calibration, the black line with little dots is our observed flow. The blue line is our simulated flow. And you can see that, you know, the model is not performing great. And so what we do is we calibrate the model to get better agreement between simulation and observed. And so all models require training data. It doesn't matter whether it's a machine learning algorithm or an HMS process-based model. So all we're really doing during the calibration process is training our model on data sets. Now the hope with process-based models like HMS is that because we have processes that we're modeling and physical processes that we're modeling is that we need less training data. Calibration and the modeling process. So this little flow diagram I just put together, and so what most people think of when we talk calibration is this parameterization piece. But what I often want to do when I talk about calibration, and what I often see is we need to come back around often and reconsider our data input, our raw data, and our method selections. So before you reconsider those, if your model's not performing well, I wouldn't try to do this parameterization step. So let's just talk a little bit about that. So this would be, consider the model formulation is data gathering, but I think we should consider it during calibration. So yeah, if your model's bad, especially really bad, definitely recommend going back and reviewing your data. Boundary conditions actually are probably the highest amount of uncertainty out of anything in your model. And so things to consider is, one, just take a look at the accuracy. I mean, often I've tried to calibrate models, and then once we go investigate one particular gauge, it's consistently bad. And so that would be time to throw that gauge out. Other things to consider with the raw data, spatial and temporal extent, spatial and temporal resolution. So what is like the time step of your boundary conditions? And, you know, does it cover the extent that you're trying to model? And so things like, you know, if you have a forecasting model, calibrating it with daily PRISM data probably isn't the best idea. So you may want to make sure that the model is being calibrated to data that's going to be similar to what you're using in the forecasting context. All right, let's talk a little bit about modeling methods. So I mentioned event versus continuous earlier. It's worth bringing up again on this slide. So modeling methods are just the methods included in a model. And one of the biggest ones we see come up again and again is event versus continuous. So often a model will be set up to do event modeling, and somebody will try to apply it for continuous. The reality is continuous is not just a single event, but often multiple events. And when you have a continuous model, you have to consider more pieces of the hydrologic cycle. So precip on a basin isn't enough. We need to have evapotranspiration and soil moisture and base flow to truly capture a continuous simulation. So that's often this, you know, this formulation step is just looking at your model and how it's set up, and is it capable to model what you're trying to do. So other things to consider, just the regional performance of the modeling method, often, and then physical basis. So some districts have a history with a particular method, and they know the parameters in their region. So if that's the case, that's probably a good method to use in your region. And then, especially if there's institutional knowledge, if you can go to a senior hydrologist at your district and say, hey, like, is this reasonable? How should I adjust these parameters? That's usually valuable. So definitely a consideration. And then physical basis. So just with physical methods, often the parameters are kind of tied to physical measurements, or they're supposed to be. So things to consider there. Is this physically based? How adjustable is it? Or is it empirical? Because this coefficient can kind of widely range. So let's talk a bit about parameter adjustment. This is a step most people think of in calibration. So this is when you have your model data, you've taken a look at it, it's good to go, and your methods are where you want them. This is often the place you'll find yourself in the forecasting context, because a lot of these models have already been built. And there's been years of history and tradition that have, you know, led to the decisions that were made to set this up. Like, we know this is going to do the best transform method. We know that gridded precip is the best for forecasting. So you're probably going to find yourself in this spot in the forecasting context. And so parameter adjustment is just the fine-tuning portion where we adjust the parameters to improve model output. And it's a question to ask yourself, which parameters can be adjusted and how much should they be adjusted? These are very important questions. Obviously, parameters that are really physically tied can't be adjusted a whole lot. And for lack of a better example, things like a reach length, like, okay, like that people actually do change that from time to time, but it's very physically based. So there's not a whole lot of adjusting that can be done there. Other parameters like TC&R, you know, for your transform, those have a pretty big range of adjustment. But then again, there's a limit to that. And so it's just really you as the modeler need to get a feel, especially in your region, like what should these parameters be and what's a good range on them. And so one of the best ways to get a feel is to do some modeling and train your data on training data sets. So run it for events that are similar to the types of events that you'll encounter in forecasting. So here's some guidance on calibration. You want to work from upstream to downstream. You want to make sure that your headwater subbasins are calibrating, because there's no sense in trying to calibrate something downstream if the upstream is not calibrated. That's pretty intuitive. And then adjust one parameter at a time. This helps you isolate and get really good control on your experiments, because you're just kind of making adjustments, experimenting. Okay, is this doing what I want it to? And so when you change multiple parameters at one time, it's easy to get confused as to what's causing what. And then adjust uncertain parameters. So things that have a range like TC&R, like you want to start focusing on those, adjusting those, do a bit of sensitivity analysis, and seeing how much does this change the result. Look for physical evidence. So something like a loss method, you want to, so if you increase your constant rate, so you increase the rate at which water percolates through the soil, is it bringing down the peak? So you want to see that what you intuit by changing the parameters is actually happening in the model. And then beware of tendency to adjust only parameters with higher individual impacts. So this is what's called in the model world overfitting. So if you see, oh, okay, like if I start adjusting this base flow coefficient and I really crank it up, I'm getting a better result in this model, even though it seems like, it might be out of range or it's a little bit too much, but it gives me a good result. The reality is that when you do that, if you try to apply that model to, say, a different event, it's very likely now that that next event is going to be, very wrong. So it's important to not overfit the model. Okay, so I distinguished event and continuous a little bit earlier. Once again, event it's something on the order of days, maybe a week, so like 7 to 10 days at most. The point at which other hydrologic processes start to come into play, things like base flow and evapotranspiration, like if you're modeling long enough for those processes to come into play, then that gets into continuous calibration, and that's when you need to start modeling those processes in your model. And so with event calibrations, these are usually focusing on the peak. What is the peak amount? Emily's going to show these. The timing, like what is the timing of the peak? And then the volume for the event. With continuous calibration, the focus is often on volume, and then we use performance metrics. It's often hard to view the entire, because with event calibrations, we're often doing a graphical inspection, where we just look at the hydrograph and we look at the fit. With continuous calibration, it becomes more difficult to do that type of inspection. So that's where performance metrics really help us there. And then for really long continuous calibrations, we might start looking at flow frequency curves and seeing if we can reduce the flow frequency curves or reproduce the flow frequency. So it's really just a matter of getting things into a view that we can process, like a flow frequency curve. We can't look at the fit for the entire 60-year simulation of a continuous model, but we can look at a flow frequency curve, can look at performance metrics. And then the last bullet point here, in both cases, performance metrics will be used to quantify performance. So graphical inspections are great, but performance metrics are kind of a common way to communicate model performance. So you can, one person can look at a curve and say, I think it's good. And then the next person says, no, that's not a great calibration. So there's some subjectivity there. The thing that we get with these statistics is a common measuring stick for how the model performs. So we tend to use these statistics in both continuous and event, and anytime you're putting together a report, it often, you'll have a list of these statistics and how each calibration location performs. So statistics that I guess all of these are usually used in the reports. There's two that we often look at, and I think most of the modeling community, at least the use-based community, looks at while doing calibration. Those are the Nash-Sutcliffe efficiency and percent bias. But we'll go ahead and mention the others because you'll probably be doing a report at some point where you'll want to include them. So the coefficient determination R-squared, you probably remember this from a college-level stats course. Let me just refresh you. So an R-squared of 0 is that the model can't produce observations. An R-squared of 1 reproduces observations with no error. And then somewhere in between is the extent to which the model reproduces observations. So I have a slide here and a couple of slides where we'll show reasonable or will qualify the metrics. So what's a reasonable or good range for these statistics? The Nash-Sutcliffe efficiency indicates a correlation of computed values and agreement of the mean. So this is really just the fit. This is the metric for how well the curves fit, the simulated versus observed. Nash-Sutcliffe efficiency of 1 is a perfect match between computed and observed. Nash-Sutcliffe efficiency of 0 is that the computed values are as precise as the mean of observed data. So that's really getting into pretty bad territory. Your model is not as good as just taking the mean of all of the observed data and projecting that forward. And then less than 0, we're getting really bad. So the mean is a better predictor than the model predicted. Root mean squared error, standard deviation ratio. So the metrics, these metrics all came from a paper, and this is one of, it's called Moriesi et al. 2007. There's a reference here in a couple of slides. And so this is one, kind of a new statistic they proposed. And so we often use it in our reports. The optimal value is 0, which means 0 root mean squared error for the perfect model simulation. And then lower RSR values represent better model performance. So this one, the first two I showed you, coefficient of determination and the Nash-Sutcliffe efficiency, the perfect good value is 1. For RSR, the perfect value is 0. And then let's take a look at percent bias. And we use percent bias to give a notion of volumes. And so this measures the average tendency of simulated values to be larger or smaller than observed values. The optimal value is 0, and then negative, positive indicates overestimation or underestimation. So is the volume greater than or the volume less than? And then here's that table I was talking about. So with each of these statistics, this Moriesi et al. Paper 2007 published these ranges as qualifying each of the statistics in a way. So very good, good, satisfactory, unsatisfactory. I think this has been passed around a lot. So if you haven't seen it before, you've seen it now and you have these slides. And so hopefully you can use this as a guide when taking a look at your model and how it calibrates. So there's those references I mentioned in case you want to go take a look. And now I'm going to pass to Emily. All right. I can't hear Emily now.
Well, thanks, Tom. And as Ann mentioned, I'm Emily Moe, and I'm from the St. Paul District, and I have a lot of experience developing our HMS models. And so what I'm going to share today is kind of some tips and tricks when you're learning HMS, because I've helped a lot of folks kind of get more familiar and learn how to calibrate. And it seems like it's a pretty good approach if you kind of break it down into 3 questions when you're just getting started. 1, what am I doing? And then where do I start? And how do I adjust or calibrate these parameters? So first of all, what the heck am I doing? It's really helpful when you're preparing to calibrate a model to set goals. Some of the calibration goals you might set would include a quantitative goodness of fit using some of the statistics that Tom talked about. Other goals would include how important it is to your model and the objective of your project to capture the timing, the volume, and the magnitude of the calibration event. And we've got some examples of goals included in the next few slides, but these goals can definitely vary depending on the purpose of your project. So First of all, it's great to set some quantitative goals using statistics instead of simply using the eyeball test, because like Tom mentioned, what looks good to one person might not look as good to another. So by leaning on these statistics and setting goals such as the R-squared or the Nash-Sutcliffe, which is what we kind of rely on the most in the St. Paul district, it's a lot more clean cut as to whether or not this is an acceptable calibration or not. So for example, to be considered satisfactory from this table, the Nash-Sutcliffe coefficient should be greater than 0.4, and if it's above 0.65, it's considered a very good fit. So thankfully, if you have observed flow data linked to a junction within HMS, HMS itself will actually compute several goodness of fit statistics for you. And these statistics can be found in the junction summary table by right-clicking on the junction and selecting View Results and then Summary Table. So for example, here you can see that there's the Nash-Sutcliffe there. And this particular location and event has a Nash-Sutcliffe value of 0.887, which would fall into the very good category. So technically, this is a statistically good calibration here. So beyond simple statistics, it's also really useful to set calibration goals for other event components that are based on the objectives and needs of your project. So for example, up here in St. Paul, for our SWIMS HMS models, we've kind of set an initial goal of calibrating the timing of events to within 12 hours of the observed peak. Again, the timing goals can vary significantly based on what the objectives of your project are. So if you're not doing a SWIMS model and you need things to be more exact, they might be a little more refined. But HMS makes it really easy to compare the modeled and observed peak timing by displaying both timestamps within that summary table window as shown here as well. All right, so volume is another key component of each calibration that you should take into consideration when you're setting your goals, particularly if you'll be using the HMS model for SWIMS or for other reservoir studies. The event volume is a critical component that you'll want to capture as closely as possible. And up here in St. Paul for our SWIMS models, we set an initial goal of capturing that total event volume within 10% of the observed event volume. And again, HMS makes it really easy to obtain the modeled and observed volumes for the event from directly within the summary table at each junction with observed data. So event magnitude is another component that you might consider setting calibration goals for. Often the peak magnitude corresponds to the peak stage and inundation levels, so depending on the scope of your study, the magnitude goal may vary. Up here in St. Paul for our SWIMS models, we set an initial calibration goal of coming within 10% of the observed peak magnitude. And again, looking at the summary table, HMS makes it really easy to do a quick peak magnitude comparison between the modeled results and the observed values if you have that gauge data linked to the junction. So the HMS junction summary table provides a lot of really great information that's available really quickly after you run your model. However, it won't compute the percent differences or alert you as to whether or not you're meeting your calibration goals that you've set. So one thing that I've found helpful is to use a spreadsheet that's set up to manually enter in your results, but then the spreadsheet is programmed to compute the timing or the percent differences, and it's color-coded to show green if you're within the range of your goals, or red if there's still work to do, like the magnitude shown in this example. But after, so we can quickly just pop that into the spreadsheet and see, oh, we've got some reds, so we've got a little bit more work to do. And if we adjust it a little bit more, we've brought it back into within the range of our magnitude goals there, and we're meeting the rest of our goals. So everything's all green and looking good. And I found that kind of developing a spreadsheet tool such as this, especially if you have a large watershed where you're looking at these percent differences and timing comparisons for several locations, it's really nice to kind of have this ready where you can just type it in and instantly know instead of having your hand compute it over and over again. And it's also really useful for documentation and for reporting purposes as well by providing a consistent template with all of the key information from the calibration present in a glance there. So once these calibration goals have been set, where does the modeler start the calibration process? And for this, there are really two main options when using HMS. One, you can use HMS standalone, and by standalone I mean you're launching the software program outside of the SWIMS CABI for calibration purposes. Or you can actually launch and use HMS directly within the CABI too, using zonal calibration, which may be more common for daily SWIMS forecasting efforts. So when you're using HMS standalone or opening it outside the CABI when you're calibrating, it's really useful to group subbasins and to calibrate by computation point. So as Tom mentioned, it's good to start at the headwaters of your watershed. So here's an example up in the headwaters where there are 3 subbasins that are above a gauge location. And it's helpful to group these subbasins by flagging that gauge junction as a computation point. And to do this, you can simply just right-click on the junction and select computation point. And this then turns the junction icon to a red shade, which denotes that it's been marked as a computation point. And flagging this junction as a computation point then groups these subbasins that are located upstream of the junction together into a group that's associated with this point. So now that you've flagged this group, you can access the parameter tables by method. And right here, we're going to look at the transform method, which in this instance is mod Clark. And by selecting this, it launches a table dialog with all of the subbasins and their associated transform values listed. And from here, the subbasins can then be filtered through the Show Elements option by selecting the computation point that we just flagged from the drop-down menu. And filtering by computation point then displays only those subbasins that have been grouped to that point. So in this case, it's the 3 that we were just looking at. And what we see here are the initial values that were estimated based on some sort of analysis, whether it's GIS or previous model values or whatnot. However, these initial values are really just an educated best guess of what these values may actually be before calibration. So a good next step in this process is to adjust these parameters by group instead of adjusting each subbasin individually. Adjusting by group allows the subbasins to maintain the scalar differences that were derived from those initially estimated values. So for example, if subbasin A was twice as large as subbasin B, and the initial estimate of the subbasin A travel time was about twice that of subbasin B, if we scale the travel time values, the TC values by group, then the final TC value for the larger subbasin will still be about twice that of subbasin C, the smaller one. And we'll simply have scaled those initial values to best match the observed data. We still maintain the approximate differences between those subbasins that were originally developed. So this approach often works really well when there are several subbasins that are upstream of a single gauge, and there's really no intermediate observed data to justify adjusting them individually. So in order to scale these values as a group, you can simply highlight the parameter column and then right-click and select Fill. And from here, you can adjust by a number of factors. To scale all the subbasins at once, you can select the Multiply by Constant option and then OK. And then from here, you can kind of just continue adjusting those parameters by computation point group until the calibration goals have been met. So another way to approach a calibration is to access the HMS model from within the SWIMS CABI using the Combined Parameter Editor. So this Combined Parameter Editor, it provides a way for the modeler to adjust parameters that also by groups of subbasins, but in this instance, those subbasin groups are called zones. Zones can be set up to include any group of subbasins Ideally, each zone would be composed of subbasins with similar characteristics and that behave similarly during rainfall events. One good way to approach setting up zones is by gauge, so similarly to how we selected the computation point grouping in the last example. So defining the groups of subbasins within each zone allows the modeler to scale or modify the entire group of subbasins in the same fashion all at once. So for example here, in the top window, we're working in the downstream West Hope zone since we have that row highlighted. In the lower window, all of the subbasins that are assigned to that zone are shown, along with their base values of the loss parameters. And these base values within the CABI typically come from the original HMS calibrated values. The combined parameter editor then allows the user to adjust these base values all at once within the entire zone. And this can be done by specifying a new value, such as 1 inch on the upper example there for the initial deficit, or the user can factor those base values. For example, over on the right, we're factoring those constant loss values by 0.5, so we're cutting them in half. And the adjustments that get made in the upper window are then reflected in the final value columns in the lower window. And these final values that are shown here are what will then be used to do the HMS computations within the model when it runs next. The combined parameter editor also allows zonal overrides for a particular subbasin if you think that that particular subbasin may need additional individual adjustments. And this can be done by selecting the override box on the far left side of the lower window. So now that we have calibration goals, we know where and how we might be calibrating the parameters, but how and which parameters do you adjust during calibration? For this example, we'll look at some of the key calibration parameters from some of the most common HMS methods that are used in SWIMS models. This includes the Mod-Clark transform method with TCNR and the deficit and constant loss method with the initial and constant loss parameters. So when you're first learning how to calibrate an HMS, modelers can often see the observed and modeled hydrographs and identify elements of the modeled hydrograph that you need to adjust and update to better match the observed data. But it's hard to know which parameters that you might start adjusting in order to better match that observed data. So for example, here we can see that the modeled results in blue are similar to the observed data. We've definitely got 2 peaks, just like the observed data in black shows. And we can see that the hydrograph needs to be shifted further to the left, but when you're just getting started, how do you know which parameter to adjust to bump it further to the left and get the timing better? It took me quite a long time to really understand which parameters provide what responses. And once I figured that out, I put together kind of a cheat sheet that actually illustrates the responses of adjusting the different parameters. So the cheat sheet can be a really great reference to a new modeler to help them decide which parameters they might need to adjust and when. So for example, here we're looking at the Mod-Clark transform parameters. We can see that increasing the TC value translates the hydrograph forward in time, and decreasing the TC value translates it backward. Increasing the storage coefficient, R, increases the available storage within the subbasin. So it generally decreases the peak and attenuates the volume further out into the future. So essentially, it's the same volume throughout here. There's no losses. You basically, if you took your hand and just squished it down, that's kind of like increasing the storage value does to the hydrograph. And in the opposite direction, if you lower that R value, it's kind of like pinching it. It reduces the amount of storage, so it drives up the peak, and it brings the total event volume closer in towards the, and produces a senior or a pinched hydrograph like that. So for the deficit and constant loss parameter response examples, if we increase the initial loss, it indicates that the soil is dry and it has the capacity to take volume out of the system, and that the volume loss is happening at the very beginning of an event. So decreasing the initial loss indicates that there's less soil capacity, perhaps it's already totally saturated, and therefore more volume goes into the initial part of the hydrograph. The constant loss rates affects the magnitude of the entire hydrograph throughout the whole event. So increasing that constant loss pulls more volume out of the hydrograph, which reduces the overall peaks, and decreasing the constant loss rates has the opposite effect and increases volume and peak magnitude. So the cheat sheet parameter response diagrams kind of provide a good idea of which parameters might require adjusting throughout calibration. The goal is to kind of just continue those adjustments one at a time until the calibration goals have been met. And don't forget to stay within realistic ranges of each parameter. Certainly make sure to revisit the final calibrated parameters and ask yourself, do these make physical sense for the basin? If not, is there a reason why? Is it like a highly urbanized area, or is there an extreme soil condition or something that would explain that? So in summary, it really helps to set calibration goals that are reflective of the scope of your project. Scaling the group by group or zone is a handy way to calibrate several subbasins at once and still maintain spatial parameter variability. And consulting the parameter response cheat sheets can be helpful to new modelers to determine which parameters might require adjustment during calibration. And that is really, those are really all the tips that I had. So
yeah, let's just talk a few special cases and tools. I'm coming from the development perspective, and still a lot of work to be done here, but we'll just show you some of the things we have now. So the graphs and the summary tables that we show and we have in HMS are great. One of the limitations is they're for a single point only. So I pulled up, this is Mike Bartle's Truckee River project, and I pulled up some results for Reno. So a common thing that we get asked is how to view these things for the entire modeling domain. And so one of the things we took a step to do is add this statistics report. And so it's in, I think it was introduced in 4.6. So reports, statistic reports. I have my run selected, water year 2017. So C, I'm just going to save this out. Generate it. And so what this is going to do is it's going to loop over all my calibration locations that have observed flow, and it's going to run statistics on all of them. So what I should get is a nice report that looks like this. So for each calibration location, you can see I have the computation point, and then I have my statistics, all of the ones that we went over. So that's nice. It's something we often do as part of the reporting process, so this just streamlines that. I know for ongoing model calibration, you're doing calibration runs and you want to see these statistics, it's a little cumbersome right now. One of the things that I'd like to see in the future is for this to become a table, much like this right here. And so with every simulation run you do, it automatically updates. So I guess we always have at HEC, we frequently do our sales pitches, so that's one of them. If you think that would be cool or you're interested in something like that, you can work with WMIST or somebody to find a way to fund it. Another thing that we've talked about is maybe color coding some of these locations in the model themselves based on how the calibrations come out. So this gives a spatial notion. There's all these different spatial points, so spatial notion of how the model is calibrating. Another kind of special use case is that the reality is that these statistics that are calculated in HMS are for the entire duration of the simulation period, and they're calculated at the simulation time interval. So often people want to adjust the computation interval for the statistics that's something different than the simulation time interval. What we did a kind of like a annual volume type study in the Northwest, and so we had I think we had like hourly flow data, but we only had daily precip data, and so we kind of wanted to normalize the statistics to the day. And so what we developed for that case was this calibration aid. You might have seen it's kind of gone around as well. And so what this allows you to do is compute those statistics at whatever interval you select. So you can't even run an HMS model at a monthly time step, but if you wanted to compute, say, reservoir inflow volumes for the month or how the statistics compare, then you have that option here. And then the other thing that you can't really do with HMS, but you could potentially do with this tool, is just adjust the extent of the statistics calculation. So often for like a snowmelt water year, we're running from October all the way to September. But the real focus of the calibration is between January and May, June, July. And so I can do things like cut the time window down here. So I've just focused the statistics onto the period that we're interested in, which I did here is January to May. So I can compute those statistics. Here's the statistics table. Once again, this is just a point location. You can open up a bunch of them, but just a single point and the tool, and then I can view these monthly average, how the volumes compare. So those are just a few extra little tools you might be interested in if your situation needs it. All right. So with that, I think we can go to questions.
I'm going to ask a couple questions that have popped up on my screen. I think some of them are to everyone, but some of them aren't. So one of the questions is, I think Tommy might be answering this one. Do the summary statistics have published standards for time steps smaller than a day, or is it acceptable to use the one values for smaller time steps?
Yeah, let's take a look at that. So here's the table. Right, so the published, you see there, it says daily or weekly time step. Now, one thing that you'll notice is as the time step decreases, these ranges only get more relaxed. So we just went from, if you're doing monthly time step, good is 0.75. If you're doing daily, good is 0.65. So what I usually tell people, there is not published ranges for that, although there has, Moriarty and that group have put out another paper or two, so it's worth consulting there. But I think the last time I looked, they didn't try to publish anything for less sub-daily. So what I usually tell people is if you can meet this criteria, you're good, because these things are only getting more relaxed. If you went down to a day, it might be something like 0.55 or something if you extrapolated this. So I always tell people just shoot for the daily criteria, and if you're doing, if you're running your statistics at the hourly level, you'll be good. If you're not good, you're going to have to do some justifying. So if you're at, 0.60 here for your hourly, then I think in your report you'd have to say, give some reasons why, But if you hit this, no one's going to ask questions.
And then, Tom, are there ways to, cut and paste calibration, incorporate setting calibration goals within HMS to avoid having to manually type them into a spreadsheet? Or you talked about having your report, but can you copy and paste values from some sort of window
let's see.
file?
I mean, yeah, if you're using a spreadsheet, you're kind of acknowledge it's going to be a bit of a manual process. Trying to open HMS here. Let me get this guy back over. I pulled it all together. I don't know how well these tables copy and paste, but yeah, I'm not able to grab that. So it looks like you'd have to type that in. So yeah, these are all things that could get better in development, and things I think we should work on as a community, modeling community in the future is creating some sort of table and adding a clipboard option where we could grab everything on the table, do whatever with it.
Okay, super. We have a question here. When you're using Clark's method, often the ratio of R over TC plus R is regional constant. Are there any plans to have HMS compute that ratio instead of computing it yourself outside of HMS?
Yeah, that's a good one, and that is true. Often those R or GCR plus R relationships. It's not. I don't know that we can do that exactly right now. There's something in development. Let's see if this version of HMS. I have a development version pulled up here. So this is trying to work around WebEx. Let me grab the window. So this is the the new expression calculator. So you can see I have a global editor where I can, well, I have a single selection. Let me close this. Not select a subbasin, so I just had a subbasin selected. Let me do transform mod Clark. So now I should see all of my TC and Rs for all of my subbasins. And then I have this calculator. And what I can do is I can calculate a time of concentration for all subbasins. Now, there's the one thing that's not in this version that will be soon is I can do calculations based on grids that are in my model, so I can sample those grids. I can do calculations based on statistics, so things like longest flow path. So if my time of concentration, let's just try it real quick. Time of concentration, or longest flow path, that's a good one. This is a dev version, so I hope it works. Actually, no, I haven't. Well, that was actually pretty fast. So there you can see I've calculated my TC. The next piece that we're going to add is it's a tab called Fields, and what Fields allows you to do is look at fields that are to the left and right of the column you're trying to calculate. And so I could potentially put in this box down here any formula I want for calculating a particular field. And so then the next question that people ask is like, are you going to have standard equations built into this calculator? And I think that's a great idea. So R over TC plus R is something that we could enforce in the expression calculator.
All right. At times when you review models, it's nice to have some of the physical parameters that were used in developing the original model. For example, knowing the length and slope of the routing reach can help make a determination if the routing parameters were reasonable. Are they computed as part of the HMS process, and can they be stored as metadata somehow tied to elements in the model?
Okay. So I think you're asking something similar to what we've recently added as well. We have subbasin characteristics, and so I just showed the expression calculator, which references these characters. This is all devs too. Well, it'll be in the 4.7 beta release. It's soon to hit the streets, but we've implemented statistics or characteristics for the subbasin, everything you see here, longest flow path, some slopes, relief, things like that. And we actually have implemented in the code some reach characteristics, so things like length, slope, relief of a routing reach. I still need to hook that up in the interface, but it'll look very similar to this. And once we have these statistics, then they're accessible through that expression calculator that I just showed that can be used in the global editors to help parameterize the model.
It's pretty exciting, Tom. There'll be a lot of learning.
I'm excited about it. These are good questions because this has been my life for like the past 3 months at least.
Oh, awesome. Okay, here's another one. I guess we have just a few more minutes here. We'll keep wheeling through them until we get the buzzer. But is there a way to color code the Nash-Sutcliffe value in the summary table based on the chart, like dark green, green, yellow, red, based on the value? You can also see where it might be good to input to the summary table where it's stated in Word format the satisfactory level, like Nash-Sutcliffe's very good, good, satisfactory, unsatisfactory.
Okay. Yeah. Yeah, so a qualification in the table. Good questions. We've considered doing that, and one of the things that always comes up, because it can be done and should be done at some point. The consideration, though, is that we want to give the user some control over those ranges and color codes and things like that. So with this statistical report, I did just use the Moriarty values and ranges and colors and documented it. So I said, when you run this report, this is how it's going to look. Now, in the future, I would love for this editor to give the user some control. So how do you want to then, and certainly one of the default options could be the Moriarty ranges, but I think we need to give the user some control because different circumstances dictate, different needs. And so for the user to say, hey, these are the bends I want to put my statistics in, and these are the color codes that I want to use. I think somebody already said I'm colorblind and this table's hard for me, you know, so things like that. Give the user some control over that. And I definitely, like I said, I would love to see this. This is just HTML table that we're writing out as output, but I would love to see it as a Java table similar to what we see here, that live updates. And maybe there's some user options or buttons up here where they can start to color code different pieces of it.
All right, awesome. Another question says, one of the early slides indicated bad rainfall as being one of the biggest reasons for calibration difficulty. If you have several storms, but the rainfall is questionable for the largest historical event, what approach would you recommend for calibration?
Yeah, I don't know if the slide said it, but I definitely said it because I see it a lot. It's difficult, especially because often around our biggest events, the data quality is the worst. Maybe because stressing the instruments. I've seen it time and time again where the biggest flows on record completely wipe out all the discharge gauges, which is just like for us who are modeling in this high flow world, you know, you say doing dam studies, like that's the data we need, and the gauges just wash downstream, you know. And so for the most critical part of our analyses, we don't have any data. So yeah, it's really hard, and it's difficult to go through. So you have 5 events, and like 4 of them are medium high, and then that really high one, you have a high one, a high precip, high flow event, and the data is just bad on it. So it's hard to pull that. You can massage the data. You can say, hey, we looked at this and we did this. But the biggest thing, if you start, so one option is just to throw it out and not use it. The other option is to massage it. The only caveat I give with massaging data is just be sure you can back up what you're doing and have really good reason for it. I know I've had to do that on a continuous study. We had to go in and reevaluate the volume for the biggest event on record, which is I was doing modeling in the Russian River, and the biggest event on record was the 1964 event. Data in 1964 is not great. So yeah, we looked around at neighboring gauges, figured out what they were doing, things like that, and justified what we did. But that's just the caveat. You can try to massage it, but you just definitely put it in your report. Talk about it.
All right, just a couple more here. We have a question about how grids are created for this model. It's probably too much to cover on this particular call, but Tom, do you want to cover or just mention how HEC is posting some of your training workshops, that sort of thing, so if people wanted to learn more, if they haven't had the intro class yet? We had one delayed.
Okay. So the question's about how the gridded boundary conditions are created, is that right? And then you suggesting that I pull up just like our training material?
That's what I was thinking, just kind of.
Okay. Yeah.
Yeah.
Yeah, let's do that. I can address the question. It might be a little out of scope, but it's a good question. Let's take a look at the training though. So yeah, we've done a lot of work in the recent past to put our training material on time. So if you haven't attended one of our courses recently, let's see. Training material, so I'm just on the HEC website. Training materials, and we put the entire prospect courses online. And so I would take a look at, there's 178 is our basic class. There should be a 369 on here, which is our advanced class. So that has all of the training materials. And then next FY, we're actually we're trying to do more and more digital online training. Like hopefully this presentation gets pulled into a video and we post it and it's there for everyone for all time. But we're hoping to do more of that with our training classes. So you'll actually have like video and the audio as well. Do you want me to talk to that question? Are there others? I can talk to it if you want.
Yeah, I think we're kind of at the end of our window.
Okay.
Maybe we'll discuss between our POCs and our division if that would be a valuable separate webinar. I think that's a little bit more than we could cover in a couple minutes. But maybe highlighting where you'd look for the gridded training. Is that in your basic HMS class, or is in that in the advanced? The advanced, I know, has a gridded section.
Yeah, I believe the advanced has a little discussion of gridded modeling methods. If they're talking modeling methods, there's probably some discussion there. If they're talking generating the boundary conditions, I don't know that there's a whole lot out there, but we could certainly, it comes from a million different sources and a million different utilities and programs, so there's a lot of different ways to do that, and
I think
probably need some more consolidated guidance on that.
Yeah, I'd say kind of pick through the process tech courses on the HMS and see if you're finding what you need on the grid production. Otherwise, you can raise questions through your POCs within the division, and if needed, we can get a class going.